Welcome back to the Deep Dive. This is the place where we don't just skim the surface of technical manuals. We really strip them down to the essential, actionable knowledge that you need.
Right, the stuff that helps you be effective and, let's be honest, pass that mandatory certification exam.
Exactly. And today, we are taking a really intensive study approach to hazardous materials, H8M. We're moving way beyond just general safety awareness.
We have to. This is about mastering the specifics.
Hmm.
How to identify a hazard, the regulatory paperwork, and the hyper-specific rules that keep a routine task from becoming a catastrophe.
A Category I catastrophe, as we'll find out.
This is absolutely foundational knowledge, and the stakes couldn't be higher. We're talking strict policy adherence here, not, optional guidelines.
So let's define it from the top. What is a hazardous material officially?
It's any substance that threatens human health, the environment, or property. And that could be because of its chemical nature, its physical properties, or even just the sheer quantity of it.
And it's not just the exotic stuff. We're talking about things you handle every single day.
Oh, absolutely. Solvents, paints, high-density batteries, aerosols, even some types of floor wax. Our mission today is to give you that structured blueprint, the rules for proper use, storage, and disposal for every single one of them.
Okay, let's do it. Tight structure, starting right at the beginning. If you don't know what you're holding, you can't manage the risk. So we have to start with recognition and identification.
The absolute non-negotiable requirement.
Right. Section 1, recognizing hazardous materials.
The foundation of all HMC&M control is information, plain and simple. If you're handling a chemical, you have to know what it is. And that brings us to the core principle from OSHA.
The Occupational Safety and Health Administration.
Right, and it's a simple cause and effect principle. If a container is unlabeled, personnel don't have the required safety knowledge.
And that immediately creates a critical failure point, a huge liability.
Exactly. So the mandate is that all HMC&M containers must be labeled, no exceptions. But the key for your exam prep is knowing what, specifically, has to be on that label.
Okay, so this is pure recall material. What are the essentials?
There are three essential items on every label at a minimum.
Okay, number 1, the universally recognized name of the material.
Yeah.
Seems obvious, but you can't have people using different slang for the same chemical.
Precisely. Number 2, the name and address of the manufacturer. This gives you traceability, you know where it came from, and you know who to call in an emergency.
And number 3, which I'd argue is the most important for immediate safety.
I'd agree. The nature of the hazard. This is what tells you instantly. Is this flammable? Is it corrosive? Is it toxic? This dictates your immediate actions.
And that leads directly to a huge policy rule, the one we see get broken all the time at busy environments.
The transfer rule, yes. The policy is absolute on this. If you dispense a hazardous material, say from a big drum, into a smaller, unlabeled spray bottle for your shift.
Which happens constantly.
All the time. You must put the exact same label information on that new container. You have to copy it over. Relabeling or just, dispensing it without that info is strictly forbidden.
Because the second you do that,
Yeah.
you've broken the chain of knowledge.
You've created an uncontrolled, unknown hazard, and that instantly escalates the risk profile of your entire workspace. It's not just a clerical task. It's about preserving that knowledge chain.
Got it. So we've got the universal OSHA standard. Now let's get more specific, especially for anyone working under Department of Defense standards.
Okay, so now we're talking about the Hazardous Chemical Warning Label, DD Form 2522. This is the really detailed breakdown you'll see on larger containers.
And what's critical to know is that you don't just fill this out by hand.
No, it's printed directly from the Hazardous Material Information System, or HMIS. It's a computer database that pulls all the data together into a structured 10-field label.
And that structure is what you need to memorize for the exam.
Let's break down those 10 fields because they go from simple inventory to pretty complex health data.
Okay, the first 5 are mostly for identification and logistics, right?
Correct. Number 1 is the chemical or common name. 2 is the hazard code. 3, and this is crucial, is the NSN or LSN.
The national or local stock number. Why is that one so important?
Because that number lets logistics and safety personnel track that material across the entire global supply chain. If there's a recall or a new policy memo, the NSN is how you find every single container wherever it is.
Makes sense. Okay, number 4 is the part number, and 5 is the item name. Pretty straightforward.
Now, fields 6 through 8. This is where the critical health and safety data lives. This is where your technical expertise really comes into play.
So what's in field number 6?
Field 6 is hazards. It categorizes the health effects. Is it acute, meaning an immediate effect like a burn or dizziness?
Mhm.
Or is it chronic, a long-term cumulative effect like liver damage?
And I see delayed effects here too.
Yes, and these are often scaled. None, slight, moderate, severe. Understanding that scale dictates the urgency of the medical response.
Okay, on to number 7. Specific hazards and precautions. This sounds like the deep dive section of the label.
It is. This is where you find special handling instructions and, most importantly, the target organ effects.
Okay, let's pause on that jargon. Target organ effects. What does that mean in a practical sense for someone who's just been exposed?
It tells you exactly which biological system that chemical attacks first. If the target organ is the lungs, it means the primary risk is inhalation. If it's the liver or kidneys, it indicates a high risk of being absorbed into your system and causing long-term damage.
So it's the difference between just general first aid and a very specific targeted medical plan.
Precisely. Which leads directly to Field 8, titled Protect. If 7 tells you what's at risk, 8 tells you exactly how to prevent it.
So PPE, personal protective equipment.
Exactly. Eyes goggles or a face shield,
Yeah.
skin gloves, coveralls, and respiratory protection, a dust mask, a respirator, or maybe even a full SCBA. This is the non-negotiable control measure.
Got it. And the last 2 fields.
9 is contact information. The company name, address, and the crucial 24-hour emergency telephone number.
And number 10 is the procurement year. Why does that matter?
A lot of people overlook that. It's a huge indicator of potential policy noncompliance. A material procured 5 years ago might predate a critical new EPA regulation. The chemical might be stable, but the rules for handling or disposing of it could be completely obsolete.
Making that older batch inherently more dangerous from a policy standpoint.
You got it.
Okay, quick recap. We've got the 3 core OSHA label requirements, and we've just dissected all 10 fields of the DoD's DD Form 2522. That's the paperwork. Now, what about the visual shorthand?
Right. The stuff you need to recognize instantly on a shipping pallet or a truck. We're talking about the Department of Transportation or DOT shipping symbols.
These are the diamond-shaped labels. Their whole job is to communicate the general hazard category immediately, using color and pictures.
And the color tells you the nature of the danger. Let's start with the most dramatic one, red.
Red means fire. If you see a red diamond, the primary hazard is thermal energy ignition.
Right. It covers flammable gas, flammable liquid, combustible materials, and explosives. Your brain should immediately think heat and sparks.
Next up is yellow. This one is a little less intuitive.
It is. Yellow signals reactivity. This is a key distinction. Red is the fuel risk. Yellow is the initiator risk.
What do you mean by that?
Yellow diamonds indicate things like oxidizing agents, organic peroxide, or radioactive materials. An oxidizer, for example, provides its own oxygen. It can turn a small fire into a raging inferno, even without air.
So a red material burns, but a yellow material helps everything burn.
That's a perfect way to put it. Now, black. Black signifies highly toxic or corrosive effects.
So poisons, strong acids, bases, things that cause direct, severe biological damage.
Exactly. Poisonous gas, liquids, solids, and corrosives. And finally, the last color is green.
Green is for non-flammable gas.
Correct. It's less alarming than red or black, but still a hazard. You've got the risk of pressure. A ruptured cylinder is basically a missile. And also the risk of asphyxiation if it displaces the oxygen in a confined space.
Okay, section 1 is wrapped. We've defined HMC&M. We've covered the 3-point OSHA label, the 10-point DoD label, and the 4 DOT color codes. Recognizing the hazard is step 1.
But recognition is useless if you don't have the playbook for how to handle it. Which brings us to the ultimate operational blueprint: documentation and control.
Section 2. Let's start with the big one, the MSDS.
The Material Safety Data Sheet. This is, without a doubt, the single most comprehensive, legally mandated document for every hazardous substance. It's the user manual, the emergency protocol, and the disposal guide all in one.
And with so many different materials out there, how is all this information managed, especially in a huge organization?
Through a computer database. For the Navy, it's the Hazardous Material Control and Management System, or HMC&M. It's part of the larger Hazardous Material Information System, HMIS.
And the scale of this is just staggering.
It is. The database contains over 70,000 MSDSs. You can't memorize all of that, which is why knowing how to access and read the datasheet itself is so critical.
And for anyone listening who's studying, you need to know the 10 critical contents of the MSDS. This is the policy compliance checklist.
Let's walk through them because they really do dictate your entire workflow. Number 1 is general information. That includes the emergency phone number. In a crisis, that's the number you call first.
Not your supervisor, the manufacturer.
Correct. 2 is ingredients and identity information, critical for medical personnel. 3 is physical and chemical characteristics.
So things like boiling point, vapor pressure, that tells you how fast it evaporates and contaminates the air.
Exactly. 4 is fire and explosion hazard data. This tells you its flashpoint and, crucially, what kind of fire extinguisher to use. You can't use water on every fire.
Right. 5 is health and hazard data. This is where you find the first aid procedures, what to do in the first 60 seconds.
6 is precautions for safe handling and use, your daily operational rules. 7 is control measures. This specifies the exact PPE and ventilation you need.
So it tells your supervisor what they are legally required to provide you.
Yes. 8 is transportation data, linking back to those DOT symbols. 9 is disposal data, which is incredibly complex. And finally, 10 is label data, which tells you what needs to be on the container itself.
And the policy isn't just that this information exists somewhere, it has to be accessible.
That is the critical compliance point. The MSDS must be available at the work center, usually through your supervisor or a local computer terminal. If it's not readily available, that's a major safety failure.
Okay, so we know how to identify it and document it.
Yeah.
Now, where does it live when you're not using it? Let's talk about stowage.
Proper stowage is often the difference between a small spill and a full-blown evacuation, and responsibility for this is shared. The program manager, the safety officer, the supervisor, everyone is accountable.
What are the key rules for storage? They seem to center on two main risks: heat and quantity.
That's exactly right. Rule 1. You absolutely must not store hazardous materials in hot areas, near heat-producing items, or in direct sunlight.
Because heat increases pressure in sealed containers, and it can accelerate dangerous chemical reactions.
Precisely. It turns a stable liquid into a volatile, explosive vapor. Rule 2 is about how you package it, especially on a ship. Materials are stored in specific cases or allotments, and you have to segregate them. Acids away from bases, oxidizers away from flammables.
And then there's Rule 3, which is one of my favorites for just pure operational safety logic.
Ah, the one work shift rule.
Yeah. Temporary stowage of hazardous material in your workspace should be limited to the quantity you need for just one work shift.
That's right.
But let's be realistic. Isn't there always pressure to just grab the big containers so you don't have to walk back to the locker later?
Of course. And that's exactly why it's a mandatory rule, enforced by spot checks. If you only need a quart of solvent for the next 8 hours, you pull a quart. If you pull a 5-gallon drum and put it by your workbench, you have just exponentially increased the potential damage if something goes wrong.
So it's a logistical rule designed to limit the severity of any potential accident.
It forces continuous management instead of staging and forgetting.
Got it. Okay, quick recap. The MSDS is the 10-point blueprint. You access it via HMIS. And for storage, you avoid heat and limit your on-hand quantity to one shift's worth.
Now we can get into the specifics.
Section 3. Deep dive into specific hazardous materials. Let's look at 3 common types: solvents, aerosols, and PCBs.
Right. Starting with solvents, they are everywhere. Varnishes, lacquers, cleaners, their main danger is their low flash point. They give off vapors that can ignite at very low temperatures.
And the risk is twofold, right? Fire and health.
Correct. The vapors are often toxic to inhale, and direct skin contact can lead to absorption. The simplest safety rule is, if you can, use a water-based solvent.
But that's not always an option. When you have to use something stronger, which too are known for being extremely flammable.
The 2 you need to know by name are trichloroethane and methyl alcohol. If you're using these, ventilation and respiratory protection are your absolute top priorities.
And there's one we need to mention that is strictly banned, but people might still encounter it in old stock.
Yes. This is critical for policy adherence. Do not use carbon tetrachloride. It is a highly toxic compound that was banned because of the severe damage it does to your organs, especially the liver.
The approved replacement for it is that first one you mentioned.
Trichloroethane, exactly. Know that distinction cold.
Okay, there's a long list of safety precautions for solvents, 11 of them. Let's run through the big ones.
All right, if you spill it, wipe it up immediately. The vapors are an invisible fire hazard.
And the rags you use?
They go in a separate, covered metal container. Solvent-soaked rags can spontaneously combust.
PPE is a given. Goggles, gloves, what about fire safety?
Have the right firefighting equipment nearby. And absolutely no smoking or open flames in the area.
Ventilation is key. If it's poor, you need a respirator.
And you store them in an approved flammable storage locker, a dedicated safe cabinet.
Two more big ones related to equipment.
Yes. Do not spray solvents on electrical windings or insulation. It can degrade them. And number two, and this is a big one, do not apply cleaning solvents to heated equipment.
Instant fire risk.
Instant flash fire.
Okay, let's move on to aerosols. The spray can. The risk profile here is different.
It is. While the contents might be flammable, the primary hazard of an aerosol can is pressure. It's a pressurized container. If you misuse it, dent it, puncture it, it can explode like a small bomb.
So the safety rules are all about preventing two things: damage to the can and exposure to heat.
Exactly. Let's run through the rules. First, ensure you have plenty of ventilation. Second, dispose of them according to your supervisor's instructions. They are considered hazardous waste.
Because of the pressure.
Yes. And on that note, keep them away from all heat sources. Open flames, sunlight, heaters. Heat increases internal pressure.
And just like with solvents, don't spray them on warm or energized equipment.
Correct. And also, don't spray them on your skin. The propellant can cause a freeze burn as it expands.
And the most obvious one?
Do not dent or puncture the container. You're basically compromising a pressure vessel. And finally, on disposal, never, ever throw them in a wastebasket that goes to an incinerator.
They'll just explode in the fire.
Violently.
Okay. Heat equals pressure, pressure equals explosion. Got it. Our third material, PCBs.
Polychlorinated biphenyls. This is a chronic toxicity hazard. They're a group of chemicals that range from oily liquids to solids.
They're used in a lot of electrical and hydraulic equipment. Why, if they're so toxic?
Because they had really desirable properties.
Yeah.
High heat capacity, chemically stable, non-corrosive, low flammability. They were great insulators and coolants.
So the very stability that made them useful is what makes them a persistent problem in the body and the environment.
That's it, exactly. They don't break down easily, and they are highly toxic. Short-term contact can cause irritation and a very specific severe skin rash called chloracne.
And the long-term effects are much worse.
Repeated exposure can damage your respiratory and digestive tracts, and especially your liver. A massive overexposure, what's called systemic intoxication, can be fatal.
So how do you know if a piece of equipment contains PCBs?
Policy mandates a specific EPA-required label. You have to recognize it. It reads, "This equipment contains PCB capacitor." If you see that label, it triggers a whole different set of special handling procedures.
All right, recap for this section. Solvents are a fire and ventilation hazard. Aerosols are a pressure and heat hazard. And PCBs are a chronic toxicity hazard that requires specific labeling.
Now let's shift from chemicals to hazardous equipment.
Section 4. We're starting with batteries. They are portable chemical reactors, and we're covering 6 different types, each with its own set of rules.
First up, the common carbon zinc dry cell.
The rules are simple. Don't store them in equipment for long periods, or they'll corrode it. Don't throw them in a fire, or they'll explode.
And crucially for disposal, don't throw them overboard. They're metal pollutants. They have to be stored in a steel container for disposal ashore.
The next one, manganese dioxide alkaline zinc, is basically the same.
Identical safety precautions. Next are the mercuric oxide zinc cells, or mercury cells. Small, high-density batteries.
These can explode. What are the rules?
4 key rules. Don't short-circuit them. Don't discharge them below 70% of their original voltage. Don't expose them to temperatures over 400 degrees Fahrenheit. And store the used ones in a steel container without puncturing them.
Okay, now for the big one, lithium cells.
High energy, high risk. They can release toxic gases or explode violently. The rules here are incredibly strict.
Let's hear them.
Use only approved batteries. Store them in cool, well-ventilated areas. Always observe polarity when you install them.
And the handling rules are basically a list of don'ts.
A long list. Do not pierce, short-circuit, recharge unless they're designed for it. Crush, burn, drop, or dismantle them. Any physical damage can cause a catastrophic failure. The phrase battery venting should trigger an immediate emergency response.
Okay, next up, the most common wet cell, lead-acid batteries.
This one is a triple threat. It has highly corrosive sulfuric acid, it produces extremely explosive hydrogen gas when charging, and it can release toxic gas if contaminated. There are 10 key safety procedures.
This sounds like critical exam material.
It is. Number 1, always keep flames and sparks away. Hydrogen gas. Number 2, ensure proper ventilation when charging. Again, hydrogen gas.
Number 3 is about the acid itself.
Handle it very carefully. We're talking full body protection gloves, apron, face shield.
4, keep the electrolyte level above the tops of the separators. 5, Use only pure distilled water.
6, and this is a key number, do not operate them above 125 degrees Fahrenheit or 52 Celsius.
7, don't short-circuit the terminals. That can cause an explosion. And number 8 is the big one, the mixing rule.
The otter rule. You always pour the acid into the water, never the other way around.
Explain why. What's the physics behind that?
If you pour water into concentrated acid, the heat released is so intense that the water instantly boils and erupts, spraying hot, corrosive acid everywhere. It's a violent geyser-like reaction. You pour the heavier acid into the lighter water to control that heat release.
A rule that can save your eyesight or your life. What's the last one?
A critical one for maritime operations. Do not put salt water into the battery. The chlorine in the salt reacts with the acid and creates extremely toxic chlorine gas.
Got it. And the last battery type, nickel-cadmium or NiCad.
Rechargeable. The rules here are about charging and storage. Never charge them in parallel, only in series.
And another key temperature.
Yes, do not expose them to temperatures over 113 degrees Fahrenheit or 45 Celsius. And never store NiCads and lead-acid batteries in the same area. Their chemistries are incompatible.
All right, that's batteries. Let's move on to the other hazardous equipment. Vacuum tubes.
2 categories here, electron tubes and cathode ray tubes, or CRTs.
Let's start with electron tubes. What's the hidden danger?
Some of them contain radioactive material added to aid ionization. If you break that tube, you've got a radioactive contamination incident.
Which means you have to follow strict radioactive material handling rules.
6 of them. Handle all tubes with care, but radioactive ones with extreme care. Immediately put any removed tube in a protective container.
And if one breaks?
Notify your supervisor immediately. Seal off the area immediately to prevent the spread of contamination. Treat all damaged radioactive tubes as radioactive waste. And if you touch any fragments, wash immediately and get a medical evaluation.
Okay, now for CRTs. The old TV and monitor tubes, the danger here is mechanical.
And it is catastrophic. A CRT is a large glass vacuum tube. The danger is implosion. You need to remember this number. A 10-inch CRT has nearly 2,000 pounds of force pushing on its face from atmospheric pressure.
2,000 pounds, that's the weight of a small car.
Exactly. If you break that glass, it doesn't just crack, it violently implodes, spraying glass, metal, and toxic phosphor coating everywhere at high velocity.
And there are other hazards too.
Yes, they carry very high voltage, a lethal shock hazard, and they emit X-rays when they're on. This means a strict set of 8 handling precautions.
Let's list them.
Always follow the manufacturer's instructions. Keep it in the shipping carton until you're ready to install it. Wear gloves and non-negotiably goggles.
And you have to discharge the high voltage before you touch it.
Absolutely. Do not strike or scratch the glass. And do not stand in front of it when installing it in case it implodes. The electron gun in the neck can act like a cannon.
Don't carry it by its neck. And if it does break?
Do not touch the phosphor coating. It's extremely toxic.
Okay, we've covered the extreme dangers of equipment. Let's zoom out now to the administrative structure for managing all this risk.
Section 5, Hazard Reporting and Risk Assessment. So you found an unsafe condition. How does policy quantify that risk? You use the Risk Assessment Code, or RAC.
And the RAC is a combination of 2 things, hazard severity and mishap probability. Let's start with severity, which uses Roman numerals.
Right. There are 4 categories. Category 1 is catastrophic. This means the hazard could cause death or the loss of an entire facility.
The worst case scenario.
The absolute worst. Category 2 is critical. This could cause severe injury, severe occupational illness, or major property damage.
Category 3 is marginal.
This may cause minor injury or minor property damage. Think of a small spill that needs a cleanup kit but not a hospital visit.
And finally, Category 4 is negligible.
This probably wouldn't affect anyone's safety, but it's still a violation of a safety standard. Maybe a misfiled label that's still traceable.
So that's what could happen. The other half of the RAC is the probability, or how likely is it to happen. This uses letters.
Correct. 4 subcategories. Subcategory A means it's likely to occur immediately or within a short period of time. The danger is imminent.
Subcategory B.
Probably will occur in time. It's not immediate, but it's highly expected.
Subcategory C is may occur in time, and D is unlikely to occur.
Right. And the power of the system is combining them. A risk coded as IA catastrophic and likely demands an immediate shutdown. A IVD risk negligible and unlikely can be fixed during planned maintenance.
It turns safety from a gut feeling into a structured, auditable policy decision.
Exactly. It links the physical hazards directly to the command's priority list.
What a deep dive. We went from the 3 required items on an OSHA label all the way to the risk assessment codes.
We did. We covered the 10 fields of the DD Form 2522 and that critical rule of limiting your temporary stowage to just one work shift's worth of material.
And we hammered home how specific rules are designed to counter specific dangers. For solvents, it's about fire risk, which means using approved flammable lockers.
For aerosols, it's all about managing heat to prevent a pressure explosion. And for batteries, it comes down to knowing those critical numbers. The 125-degree limit for lead acid, the 113-degree limit for NiCads.
And the acid into water rule, the 2,000 pounds of force on a CRT, the isolation procedures for a broken radioactive tube. All of this directly informs your daily procedures.
Ignoring these details isn't just risky, it's a policy violation. It elevates a manageable hazard straight into that category or a 2 range.
This structured knowledge is what technical competence is all about.
So we'll leave you with a final thought to synthesize all of this. Considering the sheer volume of AZMAT categories we've covered, chemical, explosive, radioactive, pressurized, corrosive, what is the single most important administrative step, beyond just recognizing the hazard, that reduces the overall risk of an entire system and keeps that hazard classified as negligible or Category Foo?
And the answer, implied by everything we've discussed, isn't just labeling. It's the consistent, non-negotiable adherence to the specific disposal, storage, and reporting requirements that are laid out in the governing manuals.
Risk management is a continuous process, not a one-time thing. You have to follow those end-of-life procedures for every material, every single day. Stay informed, stay safe, and we'll catch you on the next deep dive.